The law of conservation of momentum. The total momentum of the system is conserved if there are no unbalanced external forces acting on objects in the system. Okay, first off, let me just destroy this connection. Mechanical energy is conserved if there are no non-conservative forces doing work. This has nothing, absolutely nothing to do with this statement here. That's like asking, hey, how do you score a touchdown in baseball? It's like they're totally different games. Okay, completely different scenarios altogether. Okay, there's no connection between a non-conservative force and an external force. Okay, so just break any type of like trying to make connections there. There are no connections to be made in that. Okay, so the next thing I want to talk about is what in this world is a system thing. Okay, so a system is simply identifying what objects we're focused on. We want to know, hey, what things are what are the objects that we are looking at to evaluate this. It is you can put in your system as many objects or as few objects as you want. Okay, um, kind of the extreme case would be you could put the whole universe in the system if you wanted to. Wouldn't suggest it. You could put actually you could put nothing in your system. That would be kind of dumb, but it's not illegal. Usually in this class, we're going to put usually one or two objects in the system, maybe three, but all it does is highlights, hey, these are the objects we're looking at. Okay, so don't get derailed by this idea of system. Okay, all right, so let's consider the scenario of a bowling ball rolling and hitting a bowling pin. During the moments of impact, we're going to ignore friction. Okay, and uh, um, so we're going to draw. Is everybody okay with the fact we're ignoring friction for the moments of impact? So a free body diagram on the pin, it has a certain amount of weight, has a certain normal force, and it has an applied force from the ball colliding with it. The bowling ball, it weighs probably more. So it has its own force of gravity. It has its own normal force. And it has an applied force from the pin. Okay. Good with that? Okay. Now, what we're going to do is we're going to define the system as just the pin. Okay, we're just going to put the pin in the system. We're going to highlight the pin. Okay, so the forces acting on the pin are these three forces. Normal force, where did that come from? What object created or caused normal force? Yeah, the ground. Good. Is the ground part of the system? Nope. We just said the pin. So normal force is considered an external force because the object that caused that was not in the system. It was outside the system. Therefore, it's an external force. Okay. The applied force. Where did that come from? What object caused that or created that force? The bowling ball. Was that part of our system? Was that inside our system? No. Another external force. Okay. Force of gravity. What object caused or created gravity? The Earth. Is the Earth part of the system? Nope, we just made the pin. So all three of these would be external forces. Okay. Now, but before we start going, well, that's out, not conserved, we have to ask ourselves, are any of these forces, external forces, canceling each other out? Are they balancing each other? Are any of these forces canceling each other out? Thumbs up, thumbs down. Yes, no. Any of those forces canceling each other out? What? So those people will say thumbs up. Which are they? Good. Force of gravity and normal force. Okay. So these two are balancing each other. But is there anything that's canceling out the applied force? No. So is the momentum of the bowling pin conserved? The total momentum of the system is conserved if there are no unbalanced external forces acting on objects in our system. If the system is just the pin, is the pin's momentum conserved? No. You have an unbalanced external force, not conserved. Okay? That's kind of following the regiment of that law. But let's look at it from a conceptual point of view, kind of an intuitive point of view. How much momentum did the pin have initially before it was hit? Zero. It was just sitting there. Then all of a sudden it was hit. It was like bam. Did it have momentum afterwards? Yes. Did the momentum of the pin stay the same? Was it conserved? No. It was not conserved. It totally changed. Okay. So let's change the scenario. Let's say that we're going to include now the ball and the pin as objects in our system. Okay. We can have the same conversation as we did with the pin. We can say that gravity is an external force, normal force is also an external force, but these two forces are canceling each other out. What about the applied force? Where did this object, sorry, what object caused this? The pin. Is that inside the system? Yes. That makes this force internal. It's from an object inside the system. What about this? Like we said that this is an external force, but now that we've included the ball in the system, is it still external? Nope, it's internal now. So this idea of external, internal forces largely depends on what you include in the system. Does that make sense? So you have some freedom there. Okay, but there's wisdom. You need to apply wisdom to be able to, like, what do I put in my system? Because you just don't want to throw in everything. Okay. So the external forces, well, tell your neighbor, is the momentum of the ball pin system conserved? And tell them why or why not. Is the momentum of the ball pin system conserved? Okay. Correct answer is yes, because there's no unbalanced external forces. There's external force of normal force and gravity, but those balance each other. They cancel each other out. Same thing happens here. Now, I heard some statements. Does this force cancel out this force? No, because they're acting on two different objects. Okay? These two forces cancel each other out because they're acting on the same object. Okay? But these are internal forces. Okay? Now, So we can say, yes, the total momentum of the system is conserved. So what we're saying is this. The total momentum. So initially, did the ball have momentum? Initially, before the hit, did the ball have momentum? Yes. Did the pin have momentum initially? No, it was at rest. So the total momentum of the system is going to be the ball's momentum plus the pin's momentum. That would be the total momentum of the system. That quantity, how much momentum there is, stayed the same before and after the collision. It's just redistributed in other places. Because afterwards, did the pin have momentum? Yep, probably the ball did too. It's just been transferred. The momentum has been transferred within the system. Okay. Now, to understand conceptually why, how does the force on the pin compare in strength or magnitude compared to the force on the ball? Which one's bigger, the force on the pin or force on the ball? Tell your neighbor. Which one's bigger, force on the ball or force on the pin? All right, so I killed that. Do you guys remember the demonstration we just did? Which one's bigger? They're the same. Why? Newton's third law. Okay? So, they experience the same force. How does the time that force acted on the pin compare to the time that force acted on the ball? They acted for the same amount of time. They acted simultaneously. So they experienced the same force for the same amount of time. Therefore, they both experienced the same change in momentum. The only caveat, the only difference is one experienced a positive force, the other experienced a negative force in terms of direction. So the change, one's going to have a positive change, the other one's going to have a negative change. And this, my friends, is why momentum can be conserved, because one had a positive change while the other had a negative change, but their change is like it's still within the system. Got transferred, if you will. Good with that? Okay, so that's kind of the why momentum is conserved. Okay? So let's start applying this to different scenarios. Tell your neighbor why or why not.
force of gravity. Yeah, normal. I keep saying that. Yeah, you always like natural.
It's fine. That everybody does. Like that is.
I don't remember like natural life. Nothing is really there. It's like made forces to just cancel out gravity. So we don't have to know. Wait, no, that'd be it. So we all don't think anything.
Correct answer is yes. Why? Here's your free body diagram. In this scenario, both are external forces that cancel each other out. Momentum of the hockey puck is conserved. Next scenario. Tell your neighbor. Tell them why or why not.
I know. Yeah, but you're just thrown and you can't stop. And like, well, eventually. No way it goes on forever. That's impossible. There's an end. So space has like a wall.
Correct answer is if you just make one player system, no. Okay, you got applied force from the other player. That is an external force. It is not conserved. However, if you make both players part of the system, momentum would be conserved because that once external force is now an internal force. And looking at the other player, it has normal force and gravity cancel each other out, and that applied force, that is also an internal force. So it's just like the bowling ball, bowling pin scenario. Next question. Correct answer is, or tell your neighbor. Tell your neighbor first. Tell your neighbor. Tell them why or why not.
Because applied is helping.
Why not? What is the unbalanced external force? Friction. Okay. So it's like a. Okay.
She's trying so hard to fix it.
Oops, I got it. Thanks. Tell your neighbor.
I was thinking if I didn't have a reason to Michelle was like, no, she didn't like me because that's when she was on her. If your phone's on the desk, I'm just gonna take it. That's ridiculous. She just. I heard someone told me today about earbuds. Really? My math teacher told me actually. Probably why.
Correct answer is I got one vote for A.
Oh, yeah.
A. All right. I would agree if you sent the stick sliding across the ice and it hit a hockey puck. I would agree with that. But there's an external force on the stick from you. You are not part of the system. Okay? The force between the puck and the stick, yes, are internal. But there's other forces, you swinging it, that would be external. Now, if you put you in the system, you, the stick, and the puck in the system, then we could say momentum is conserved. Okay, cool with that? Tell your neighbor. All right, what do you say? No. But gravity, I thought that was a conservative force. It is, but that's not anything to do with momentum. That has to do with work and energy. Okay? That is an external force because the system is just the puck. What object caused the force of gravity, created the force of gravity? Earth. So, if we were to include the Earth as part of the system, would momentum be conserved? Yes. Now, that is conceptually true. If you ever find yourself needing to include the Earth as part of your system to be able to do a mathematical problem, don't. Okay, that's just going to be stupid. Okay, conceptually it's valid, but when you actually go to do numbers with that, like, don't go another way. Pick another approach. Okay, go to that. That's as far as we've got with everybody else. So, call that good for today.